Hello and welcome to IWCS webinar. And now I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today we welcome Arjen Bogaerds, Senior Scientist, DSM Functional Materials from Geleen, the Netherlands, who will be presenting his paper on high-speed fiber drawing, a resin's point of view. Arjen Bogaerds is a Senior Scientist within the DSM Corporate Research Department, DSM Ahead. He holds a master's degree in mechanical engineering from the Eindhoven University of Technology in the Netherlands. In 2002, he received his PhD degree from that same university in the field of computational rheology. Having a broad interest in the field of fluid dynamics, he started his career at DSM and, in 2007, moved to academia in the field of hemodynamics, blood flow through the human body. In 2011, Arjen rejoined DSM in the Material Science Center in the field of polymer processing. Arjen, we welcome you today to present at today's IWCS webinar series event.
Okay, thank you very much, Ed. Let's see if I can get this working. So what I would like to talk about is high-speed fiber drawing. So how to increase the speed at simply at the draw tower, and how we, as a resin manufacturer, look at those issues. So the work I will present is partially done already quite a while ago. Some things are also quite fresh. It's a cooperation within HEAD or within DSM between the business group Desotech. So we see Wai-Min and Pratik there, and what we call the corporate sciences. That's me and Marcus on the top two lists. So basically, what we do is support all the different business groups within DSM that have to do with materials productions. So let's try if I can put it down. Just here to start and give you a small introduction, and for those of you who are not that familiar with how to produce, how optical fibers are produced, this is the general layout of the system. So we have a glass fiber. It's being pulled from a preform all the way on the top. It's heated to a molten state, and then drawn pretty fast, around 1800 to almost 3,000 meters a minute nowadays, down, and while it is actually being cooled. And all the way on the bottom, you see the coating dies, and locally there, two acrylate resins are being deposited, are being applied on this glass fiber. Now, typically, we have a hard protective layer on the outside. Think about it, a resin which is after cure has a modulus of about 1 gigapascal, and a soft inner layer, rubbery-like material of inner layer of about 1 megapascal. A little bit less, a little bit more sometimes. Typically to avoid residual stresses in the glass and the attenuation that comes along with it. Now, typical fiber diameters, of course, are around 250 microns. Now, there's basically two ways how we can do that. Of course, there's the wet-on-dry system, where we have the glass fiber passes through the coating die, it passes to a curing stage, it's partially cured in that phase, and then it passes again through a coating die where the secondary is applied, and the remaining curing is being done all the way at the bottom of the tower. That's one way of doing it. The other way, what we see more and more now is so-called wet-on-wet, where we have a composite coating dies. We have the primary coating die and the secondary coating die directly on top of each other. And basically, in the secondary coating die, the fluids are flowing together through this die. So we have only one curing step all the way on the bottom. As a resin producer, we of course are interested in the relation on how resin properties relate to processing and the other way around. And that's something that is important to us. One of the things that we ran into a couple of years back was a problem that we looked at, and we called it a Rook problem. And of course, you can see why that is. We have inside under this microscopy image a glass core. You can clearly see the primary as well as the secondary coating, but the interface between the primary and the secondary coating shows all kind of non-inhomogeneities. It looks like almost there was a hook on this interface. Now, this is the result of a wet-on-wet application system. So it's a multi-layer extrusion. And what you can clearly see is that the overall thickness remains constant. And at the same time, you can also see the interface as being largely deformed. Now, we'll come back to that a bit in a later stage. Of course, from a fluid mechanics point of view, we'd like to understand how resin properties and processing properties relate to each other. So we have to really understand how the whole fluid dynamics inside this coating die is governed. So that's a physics problem. And what we see is that basically it's not an easy physics problem because all the physics that you can think of play a role. We have the Reynolds number. Basically, it tells us something about inertial forces with respect to viscous forces, which is non-equal to zero. We have heat convection. We have heat conduction, which play a role. We have viscous dissipation. So there's a lot of energy being dissipated inside the coating die and taken up by the fluid. And we have elasticity. So basically that means that locally the molecules are being stretched into a state where they really start to show elastic recoil when the stretch is passed. So the question is a little bit, how do we deal with all those issues? Because from an experimental point of view, if you look at a draw tower, it has a high velocity. Think about 30, 40 meters per second on a very, very small length scale with 240, 250 microns thickness of the fiber. And there's quite a lot of steel in front of it. So we don't have access with a microscope or with other video techniques to see how the whole fluid dynamics is governed inside this coating dies. So it's really difficult to do. Then the question is, how can we then improve the process? How can we improve the materials in such a way that we can gain access in speed? And one of the ways to do that is actually by doing a computational analysis of the flow inside the die. And using this kind of analysis, we can identify the important material parameters, the important flow parameters, and the important geometry parameters of the coating dies. And of course, that's nice to do everything in theory and behind the computer, but you would like the verification as well. So what we do in this case is we have Horizontal as die manufacturers who helped us making the designs that we came up with, and do the verification in-house on the Nextrom draw tower simulator that we have in Arjen. So talking about these modeling efforts, so what do you need for that? It's really a very powerful tool for the analysis. We need a computer, sometimes a big one. You need a software, of course. You need a finite element kind of fluid dynamics software. But the other important factor that is in there is really the resin characterization. So how does the rheology of the material look as a function of different deformation rates, different shear rates? And do we see viscous behavior? We look at the viscosity. Do we see elastic behavior inside the fluid? Look at the models. But what you get out of it, the parameters that can be accessed is quite a lot. Because now, of course, we do the analysis, and what we get is a temperature distribution, velocity profiles, and from the velocity profiles, we can also access streamlines. Basically, that's the path that all the molecules are following through when they pass through the coating die. We can access the pressure distribution, local shear stress that is acted on the fiber, resistance time distribution. And what's more, if we look back at this hook problem, we can also look at flow instability. And that's an important factor, especially when you go to high speeds. Now, just as if you look at these finite element methods, one of the key ingredients there is a finite element mesh or a finite element grid, sometimes it's called. And what I'll show you is some results of a coating die, typically what you see on the right top, the small insert there. But we don't do this in a three-dimensional fashion. We consider only one cross-section of this coating die, as you see in the image below, and then assume that over the circumference of this coating die, everything remains equal. And in practice, that is a very normal assumption, which holds to be true. Just a little bit about the resin rheology, because now we have a primary and a secondary. And what we typically see is that they have different rheological behavior. The simple way to look at it for me as a non-chemist is simply like this. We have functionally acrylated oligomers. There's a photoinitiator. We start to build a network upon the UV incidence. And you can imagine that typically the primary coating, which has a low modulus, a low cross-link density, has a relatively high molecular weight oligomer structure. Typically, high molecular weight molecules relate to elastic effects because they simply stretch further and easier than the shorter molecules, which tend to behave more Newtonian. I actually see that back if you look at one of the things that we put in the model. So typically the resin rheology, and there's a number of things that you can see here. Of course, you see a Newtonian plateau, which is the horizontal lines that you see for each different temperature, and now we plot here the shear rate or the shear viscosity as a function of the shear rate for different resin temperatures. And what you also see is the typical non-Newtonian behavior that is induced by the fact that we have these high molecular weight oligomers in there. And you can see that typically being expressed as this shear thinning behavior that starts to induce at a certain shear rate. So the moment that it starts to deviate from its Newtonian plateau, that also gives us an indication whether material typically starts to behave in an elastic fashion. Now, there's on the bottom, there's a last line, but that's a pure technical one. What we do is we cannot just plug these values in the models that we use. We first have to transfer this into a viscoelastic constitutive model. And what we used here is a two-mode discrete spectrum Leonov model to describe the viscoelasticity of these materials. Now, if I do the finite element analysis, typically they showed the grid before, but let's start with a fully functioning system. Here, what I do is we vary the draw speed, so slowly ramping up and keep everything constant. So the temperature is constant, pressures are constant. And typically, from a theoretical point of view, this is really a very nice process because it's a very self-regulating system. You can see you can slowly ramp up. Without any other external influences, and we can do that in the model. And you can see that the geometry of the primary coating remains almost constant within 1 micron fluctuation. The question is, what happens now in real life and at high speed? Because however nice this picture looks, in practice, things will be different. If we look at the inside of the coating die, we first have to do that. One of the things that we observe is really a very nice or a very big vortex. So we take again the finite element grid, and what I'm now plotting here are streamlines. So basically, those are the lines that the fluid is following when it passes through the coating die. There's two colors, blue and red. Of course, it's not blue and red, but it's just to indicate the difference in the streamlines here. Typically, this is the entrance, or the right top is the entrance of the resin, and you start to see it. You follow the blue lines all the way when it leaves together with the glass fiber, the exit at the bottom. Now you also see the red lines, and the red lines are basically closed streamlines. So they don't have a beginning, they don't have an end, but they just keep on circling around. And that means that they're part of a big vortex or a recirculation zone. And that also means that they have a very long residence time in that on that position. Now, if we then compare it to the same model to the resin temperature, where we in this case enter at 50 degrees C, and we run the machine at a certain speed, you see a large difference in temperatures. So actually, in the center of this vortex, the temperature can become quite large. And that's really typically the effect what you will see of viscous dissipation. The question is a little bit how large will it be upon ramping up, and that is something that the simulations can actually tell us. So in the bottom in this graph you see the draw speed all the way up to 3,000 meters a minute. And the peak resin temperature inside this coating die. So that's basically the peak temperature inside this vortex. So we apply the coating at 50 and also at 65 degrees C in this case, these two calculations. And what you see is that already at 2,500 meters a minute we're having a maximum temperature of about 160 degrees centigrade. And it really puts some strain on the resin where we have to work on and which we have to take into account because it cannot handle that forever. Now the other one, another consequence of high speed, and it's something that we see in practice as well. If we have a existing draw tower, we pull down the heated, the molten fiber down. It's being pulled through a cooling tube, and we want to apply it in the coating die at about 50 degrees C. But the cooling tubes have a limited amount of cooling capacity. At some point, it just you cannot go cool any further, and it means upon increasing the speed, also the temperature of the incoming glass fiber is increased. Now, if we just plot the temperature gradients on different positions, different Z positions in these coating dies, you can see for different temperatures of the incoming glass fiber also gradients in the temperature, as you see on the graph on the bottom right side. And this really has consequences, this temperature gradient, because we've already seen that viscosity, the rheology, is rather dependent on temperature. Now, if we do the simulation and look at how the coating thickness is dependent on this incoming fiber temperature, and you see that there is a big dependency on that. So this is also a reason why it would be very good if we can also monitor the temperature of the incoming glass fiber temperature for consistency in the coating thickness. But what I didn't talk about up to now is really, let's say, the transient effects, so the instabilities that can occur inside these coating dies. I showed you already the Rook problem. That's the one that we see here, where we have the deformation of the interface, but the straightness of the secondary outer coating on the outside. And maybe there's only one conclusion possible for this, and that means that these deformations of the interface can only occur inside the secondary coating die. So when the two fluids, the primary resin and the secondary resin, are flowing together through this die. And there's a hypothesis that we had at that time, and there's also a very nice experiments which you can find in literature. You can see it daily also all around you, and that's two different fluids on top of each other, for instance, with a different density or a different viscosity. And if I now put this into let's say a glass box and I tilt it slightly, what will happen is that the high density fluid will flow down, the low density fluid will flow up, and we start to generate a shear layer in between, exactly on the interface. So from an experimental point of view, what you will see is something that looks like this, and we actually call that in physics, it's a Kelvin-Helmholtz flow instabilities. That means that disturbances that can initially be initiated on the interface, they can grow along the interface due to differences in rheology, of the two different fluids. And there can be differences in density, differences in viscosity, but we also know that elastic effects play an important role. And we see that in different type of polymer processing, for instance, in multi-layer extrusion of packaging materials, where you have different layers on top of each other of polymer melts, you see very, very similar effects. So if we translate that back into this Rook problem, where we have this non-straight primary-secondary interface, we can think about how the differences in rheology influence these type of instabilities. The other question is, let's say we keep the rheologies the same, but can we do something with the geometry or the way that we are applying these coatings on top of the glass? And to give you a bit of a flavor of the analysis that we do for that, it's not a finite element analysis, but we do it slightly different. We simplify the problem into having a fiber, having a primary inflow, having a secondary inflow, and of course there you have a fluid-fluid interface, and having just a very large parallel session where the two fluids flow together. Now we have to make it a little bit more accessible, we now have two flow phenomena happening at the same time in this coating die. We have a drag flow, simply induced by the fact that we have the fiber pulling the fluid through the coating die. But at the same time, there is a pressure gradient which is actually pushing the fluid back. So the total flow will look as a sum of, let's say, the two pictures that I show on the right side of this graph. So then if you want to know something about the transients, about the dynamics of these type of flows, the typical way what we do is do what we call a generalized eigenvalue analysis. And the way that works is simply by computing a steady state flow in terms of velocity fields, pressure inside the die, and the polymeric stress inside the die, and then expand this steady state flow field in the streamwise direction. Now, there's a few things that are important here. So what we do is we analyze a perturbation of a certain wavelength, of a certain length, and then for that length, we compute what we call the eigenvalue spectrum, and that's this red sigma that is there. And the maximum of the real part, this is a complex number, the maximum of that real part denotes whether something will grow or whether something will decay. So if this is larger than 0, it will grow, and if it's smaller than 0, it will simply decay out. So fluid dynamics is all about putting a perturbation in and see whether it grows or whether it decays. But the important factor here is this alpha as well, because we put in a certain wavelength, and which is denominated here by 1 over alpha. Now, typically, what we get out of that is something like this. On the left side here, you see an eigenvalue spectrum, in this case as a function of the wavelength, and you see that the spectrum moves through this XY plane. But for us, the interesting part is on the right side. So that is the growth rate as a function of the wavelength. So on the bottom side, the horizontal axis, you see this delta, which is now the wavelength, and the growth rate is on the y-axis. So positive is growing and negative is stability. So typically, in this, what you can conclude for this figure, for this typical example, and this is just an example, all the small wavelengths will tend to grow in this case. So now the question is, can we translate that into the real phenomena, what we see if we plug in the real resin rheology and if we plug in real geometry numbers? And what we get is something that looks like this. We again use these two discrete Leonov nodes, and we see a certain maximum of instability arising at 0.5 millimeter wavelength. But that's not so far away from the Rook distance that we see in practice. We also see that for very long wavelengths, the flow tends to be stable. So there is a selectiveness inside this coating die for half a millimeter approximately. Next question is, now I have done this for a certain geometry call this H on the right side. What happens now if I reduce that geometry to a lower value? So let's say 60 microns rather than 180 microns. Just a few examples. But typically what you see is that, let's say, the selectiveness of 0.5 millimeter moves up to 1.5 millimeter. So we go to higher wavelengths. But also the growth rate reduces. So that means that any perturbation that is induced inside the coating die by whatever reason, some vibration in the system or something else, will not grow as fast, and you will not see it as well as it was before. But there's an important other factor here. I have now gone up to 1.5 millimeters, but why should a coating die be 1.5 millimeters long? Before this work, many coating dies were approximately 10 millimeters long, so this typical wavelength fits in for a number of times. But there's no reason why it should be that long. And with that, if I now make a coating die that is only 1 millimeter long, this 1.5 millimeter instability does not fit in anymore. So I will never find it back. If I find an instability back, it will only be of a short wavelength. So this typical gives us guidelines as to how to design a coating die and how to improve on that. And typically what you see here is the result of this analysis for a secondary coating die where the primary and the secondary flow together. So we have the traditional die on the right side, and we have an improved design on the top right side. Just to give you an idea of the sizes and how that relates to each other, I told you something about the 10 millimeters. And this one is only 1 millimeter in length. So two things here: improved flow dynamics, where we are expecting to see, not to see this hook phenomenon, but also we don't have a vortex in this coating die. And the next step is, of course, we have to validate those analyses. So we have now given guidelines. We've made the coating die, but we have to validate that. And what we typically see is if we take an old existing die for these two resins, primary and secondary, we indeed see this hook effect back with a certain wavelength in the left picture at 20 meters a second. And what we see with the improved die design is a fully straight interface between primary and secondary, even at 30 meters a second. And the 30 meters a second was really the limitation of, let's say, the draw tower simulator. You can go to higher speed without seeing those hook effects. So the interface remains stable, but the question is also, what about matching rheology? Because this gives us a way to improve on the process, a way to improve on the process geometry, but also it gives us very nice knobs to turn on rheology-wise, because now we can also say, okay, now we understand how this instability works, how it depends on resonant rheology, how it depends on processing parameters. Can we now tune our material parameters in such a way that we can avoid these type of issues? And that's, at least from a resin point of view, an important factor. So as a final slide, what we see is that process robustness, there's a strong interaction between the resin properties and the hardware. You can tune the hardware in order to fit the resin properties. You can also tune the resin properties to fit the hardware to a certain extent. There's a limit to that. So there's an important consequences of going to higher speeds. So we have seen the vortex inside, and it's really getting hot, and 3,000 meters a minute for a long time, maybe too much. We don't know that yet. We also see that geometry is strongly influenced by the cooling capacity of the tower, and that's really the temperature of the bare glass fiber that goes in the coating die is critical in this case. And we can also analyze the dynamic flow instabilities that we see, and most of the time they limit the speed. So I hope I could convince you that these type of modeling tools are useful to understand and improve the processing and also, let's say, the resin properties. And finally, I'd like to thank Horst Seidel for creating the coating dies, because without him, we would never be able to validate the analysis that we did here. Okay. Thanks.
Very good. Thank you very much, Arjen. And at this time, we will take as many questions from the attendees as time permits. And I'd like to start with this first question. With large deformations of the interface using the wet-on-wet process, can you confirm that the wet-on-dry process is much more preferable for the coatings application?
So what I've shown here is that the two fluids are flowing together through the coating die. In a wet-on-dry system, it's not that different. It just only depends on the cure state at which you enter the secondary coating die. So you have to make sure that you're getting to a sufficiently cured primary in order to not have these type of deformations. Yeah, but it's different because now conversion or the partial conversion of the primary plays a role, but it's also very similar.
Okay, thank you.
The questions. Yeah.
Yes, thank you. Next question. Do you recommend an optimum draw speed and fiber temperature to maximize coating geometry consistency rather than simply to maximize speed? And then also there's a second part to the question. Does this greatly impact the overall quality and transmission and attenuation of the fiber?
So to answer the last question, we don't know yet. That's something that is that's still, at least I did not get any feedback that at high temperature incoming glass fiber temperature we affected the properties of the resin. With respect to coating or processing consistency, yeah, the best way, as I showed in the first modeling tool, is if you keep everything at 50 degrees C, you get a very nice, very well behaving system. So in that case, that would mean, yeah, you have to cool it back down to 50 degrees C. But that that means that there is a height limit on the draw tower.
Okay. All right. Next question. Can the interface instabilities even yield to bubbles, nodes, or delamination? No, I don't believe so. So there is no entrainment of gas inside these coatings. They adhere quite well. The only way that it could lead to cavitation is when you create the cavities inside the coating die, and I don't see the pressures dropping that much inside the dies by itself. Okay, thank you. Next question. Which is more important to control to assure optimum coating applications, resin rheology or die geometry?
Well, they both go hand in hand. I would not say there is one more important than the other. No, there is.
Okay.
There's a lot of things you can control with resin rheology, but you cannot control everything with resin rheology, and the same holds for the hardware configuration. Yeah.
Okay.
It's a bit of a difficult. It's a very general question to answer. I don't have a fixed answer to that one, unfortunately.
Okay. Well, thank you for the response. Next question. Considering that resin temperatures could reach 200 degrees C in your model, have you considered the role of volatility of the coating components of the flow and instabilities?
Yes. Indeed, what happens, you would expect some volatility of the individual components inside. On the other hand, but I didn't show a picture of that in this presentation. If you look at the local pressure inside the coating die, especially around the vortex, it's not under atmospheric pressure. So the pressure can go up to 20, 30 bars. And that's where you would expect volatility to not play a big role. So I don't think there is a chance of creating gas bubbles or gas entrainment under those pressures.
Okay, thank you. Next, do differences in CTE between primary and secondary contribute to coating defects?
So differences in CTE, I would expect them to be expressed in a later stage. So what I really talked about here was purely about processing instabilities where I know that they occur or they are initiated inside the coating die. If there is differences in CTE, you would expect that you generate residual stresses inside your coating geometry, and they should pop up on a later stage, so when it's on the reel or... and I don't expect that, especially in this case where you see a very nice or a very well-behaved outer diameter or outer surface of the filaments, that difference in CTE or differences in residual stresses there play a big role in that phenomenon. So if there is, I would expect that if there are differences in CTE, that you would see them that they would be expressed in a different defect.
Okay, thank you. Next question: should the primary coating temperature be set higher than the secondary to better match their viscosity?
I have to think about that for a second.
Sure.
So if there are, especially with these interface instabilities, of course we know that if you keep the rheological properties of the two resins the same, you will not see any interface instabilities. So if temperature is one way to govern that, that could be an option indeed. But you have to keep in mind that the moment that you do that and these two resins join with each other, there will be also a temperature gradient present as well. So that complicating factor in this whole system, I'm not sure if it will be let's say a stabilizing force or a destabilizing force in this case. But that's something that is, it's very well possible. Yeah, we didn't look into that.
Okay. Next question. Have you confirmed such high temperatures in the vortex?
Well, it's very difficult to confirm that in practice. So this is something that comes out of theoretical analysis together with, let's say, the rheological analysis of the resins. So we know that there is a certain amount of viscous dissipation, so energy absorbance inside the resins. How much that really is, that is also remaining as a question. But we know that it is, but we're quite sure that it's actually quite severe. And if there are any suggestions for, let's say, how to measure something like that in practice, I would be very open or willing to test that, because that would be a very interesting experiment.
Okay, very good. We appreciate all your responses, Arjen. I don't see any questions at this point, so thank you for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Arjen after today's event. Each of these IWCS, I'm sorry, go ahead.
Yeah, no, I just wanted to say you're welcome.
Oh, very good, very good. No worries, no worries. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, August 18th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 65 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader, showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 8th through Wednesday, October 11th, 2017, at the Gaylord Palms in Orlando, Florida, USA. In addition, the second annual Regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place on Monday, March 19th through Thursday, March 22nd, 2018 at the Pudong International Convention Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.